The electrostatic potential on the surface of a charge conducting sphere is 100 volts. Two statements are made in this regard. S1, at any point inside the sphere, electric intensity is 0. Okay, and S2, at any point inside the sphere, the electrostatic potential is 100 volts. Which of the following is the correct statement? S1 is true but S2 is false. Both S1 and S2 are false. S1 is true and S2 is also true, and S1 is the cause of S2. S1 is true and S2 is also true, but the statements are independent. Now basically when we have a charge conducting sphere, so the voltage across the charge conducting sphere is 100 volts, and we have the electric field intensity, which is a change in the voltage with respect to the radius, that is equals to 0. So now whenever there is at any instant there is at any point inside the sphere, the electric intensity is 0. This is correct because the electric intensity of the sphere is equals to 0. Also we have the potential of the charge conducting sphere inside the charge. Potential inside will be equals to the potential on the surface. Hence, because of the first point, that is at any point inside the sphere, the electric intensity is 0. Because of the first point, it gives rise to the second point, that at any point inside the sphere, the electrostatic potential is 100 volts. So S1 is also true. Yes, the electric intensity is 0. S2 is also true. Yes, the electrostatic potential is 100 volts, and S1 is the cause that because of which the electrostatic potential is 100 volts. S1 is the cause of S2. So we get the final answer to be C. 5 charges Q1, Q2, Q3, Q4 and Q5 are fixed at their positions as shown in the figure. S is a Gaussian surface. The Gauss law is given by E dot ds is equals to Q upon epsilon naught. Which of the following statement is correct? E on the LHS of the above equation will have the contribution from Q1, Q5 and Q3, and Q on the right hand side will have the contribution from Q2 and Q4 only. Now E on the LHS of the above equation will have a contribution from all the charges, while Q on the RHS will have a contribution from Q2 and Q4 only. E on the LHS of the above equation will have a contribution from all the charges, while Q on the RHS will have a contribution from Q1, Q3, Q5 only. Both E and the LHS and the Q on the RHS will have a contribution from Q2 and Q4. Now basically we have a Gaussian surface out here, which is this. In the Gaussian surface we have two charges, Q1 and Q2. The Gauss law states that over the total integral, that is E dot d over the total normal electric induction, E dot ds over the surface is given by Q upon epsilon naught. That Q is the charge on the, this is the left hand side and this is the RHS. So from the left hand side we have the above equation. So the charges so the Gauss law states that E dot ds is equals to Q upon epsilon naught. So the E, the electric field intensity, will in the above equation will contribute with all the charges, but the Q on the LHS will contribute only those charges which are there in the Gaussian surface. So that is on the right hand side, the Gaussian surface has got two charges, so the Q will contribute only to Q1 and Q2, whereas on the left hand side this E will contribute to all the charges. That is, we have option B, E equals to E on the LHS of the above equation will have a contribution from all the charges, while Q on the RHS will have only the contribution from Q1 and Q2 and Q4 only, as this is Q2 and Q4 only. Sorry, this is Q2 and Q4. So the correct option is option B. 3. The equivalent capacitance from the network shown in the figure is 1200 upon 7 picofarads, 1000 upon 4 picofarads, 1800 upon 7 picofarads, 1300 upon 3 picofarads. Now here we have two capacitance, they are connected in series, and two capacitance, they are connected in parallel. Those is C2 and C3. Now the capacitance C1 is equals to this capacitance C4, that is around 100 picofarads. Also the capacitance C2 is equals to the capacitance C3, that is 400 picofarads. Okay, now since C2 and C3 are in series, the equivalent capacitance is given by, we calculate the equivalent capacitance as C prime, which is equals to 1 upon C2 plus 1 upon C3. That will be 1 upon C2 is 400 plus 1 upon 400, that gives you 2 upon 400 that is around 200 picofarad. Okay, so C prime is equals to 200 picofarads. Now here C1 and this C2, C1 and this C prime, this entire becomes C prime now, and this C prime are in parallel connection. One is up, one is down, both are in the parallel connection. So the equivalent capacitance through them, again for this we take it as C double prime, which will be equals to C1 plus C prime. So C1 is 100 plus C prime is 200, that is around 300 picofarads. Okay, now similarly we have C double prime and C4 which are connected in series. So hence the equivalent capacitance, that is the total capacitance, total equivalent capacitance will be equals to C equivalent will be equals to 1 upon, that is C double prime, plus 1 upon C4, that is equals to the equivalent capacitance, that is equals to 1 upon C equivalent, which is equals to 1 upon C double prime plus 1 upon C4. So 1 upon C double prime equals to 300 plus 1 upon C4 is equals to 400. So that gives you 7 upon 1200, that is 1 upon C equivalent. So C equivalent becomes 1200 upon 7, that is the total capacitance picofarads of the capacitor. Question number 3, the equivalent capacitance for the network shown in the figure is, according to this network we have the capacitance C1 is equals to the capacitance of C4, that is equals to 100 picofarads. Also the capacitance of C2 is equals to capacitance of C3, that is around 400 picofarads. So now we will be dealing with the capacitance in series and the capacitance in parallel. From the figure we can notice that the capacitance C2 and the capacitance C3 are connected in series. So the formula, the equivalent capacitance, we can take it as C prime, which is equals to 1 upon C2 plus 1 upon C3. That will be around 1 upon C2 is 400 plus this 1 upon C2 400, that gives 2 upon 800, that is around, sorry, 2 upon 400, that is around 200 picofarads. So C prime is equals to 200 picofarads. Okay, now again C prime and C1 are connected in this. C prime, total of this, and C1 are connected in parallel. So according to that we take again an equivalent capacitance C double prime, which is equals to, for the parallel capacitances we have C prime plus C1. So here we have C prime is equals to 200 picofarads plus C1 is equals to 100, that is around 300 picofarads. Okay, so we got C double prime is equals to 300 picofarads. Now from the circuit we come to know again we have finished this much of the circuit. Now remaining the other circuit. So question number 5, 2 point charges of 1 microcapacitance and minus 1 microcapacitance are separated by a distance of 100 angstroms. A point P is at a distance of 10 centimeters from the midpoint and on the perpendicular bisector of the line joining the two charges. The electric field at that point P will be. So basically we have charge Q1 out here, we have charge Q2. Q1 will be 1 mu C and here it will be minus 1 mu C. So the distance between them D, which is separated by a distance of 100 angstroms. Okay, then at point P, a point P is at a distance of 10 centimeters from the midpoint. So from the midpoint there is a point P which is a perpendicular bisector of the line joining the two charges. So we have to find the electric field at the point P. So basically we have given here is the distance D, which is equals to, that is the length, okay, that can be 100 angstroms. Converting it we get 10 raised to minus 8 meters. Also the distance from point P to this is 10 centimeters, that gives you 0.1 meters. Now at the shortest dipole, the electric field intensity at this point P will be given by this formula, which is 2QL upon 4 pi epsilon naught r cube. So where 1 upon 4 pi epsilon naught r cube gives you 10 raised to 9 into 10 raised to 9. I am rounding up the figures. Also the distance L is given as, also the charge Q is 10 raised to minus C when compared to, when we converted it to coulombs, into the length, which is equals to 10 raised to minus 8 100 Armstrongs. We have converted it into meters. Also we come with the radius, that is 10 raised to minus 1 cube, that is in meters. So solving up the entire thing gives you 0.099 Newton Coulomb inverse. So your answer is 0.09 Newton Coulomb inverse. Two condensers. Question number 8. Two condensers, one of capacity C and other of capacity C by 2, are connected to a voltage battery as shown in the figure. The work done in charging full the both of the condensers is. So we have two capacitors, one is C, one is C by 2. They are connected in parallel to a voltage. So from this we know that the potential difference across both the capacitors should be same. So the potential difference across capacitance 1 is given by C into V, and the potential difference across capacitance 2 is given by C by 2 into V, because it is C by 2. So the total charge will be, equivalent charge will be Q is equals to Q1 plus Q2, that will equals to C by V plus C by 2 V, that gives you 3 by 2 CV. Now the work done in charging both the capacitors, that is the work done in charging both of them, both the condensers, is given by the formula work done is equals to half QV. So we have half Q is given by 3 by 2 CV into this V. Total comes across 3 by 4 CV square. So that will be the work done to charge both the capacitors. We have the option B, 3 by 4 CV square. A capacitor is made up of two circular plates of radius r each, separated by a distance of d less than r. The capacitor is connected to a constant voltage. A thin conducting disc of radius r less than r and thickness t less than r is placed at the center of the bottom of the plate. Find the minimum voltage required to lift the disc if the mass of the disc is m. Now basically we have two capacitors out here. Okay, both the capacitors are circular plates with the radius r. They are separated by a distance d. Okay, and there is a thin conducting disc of radius r which is kept at the bottom. This is having a small radius r. Also it has a thickness which is much less than the small radius. Okay, find the minimum voltage. We need to find the minimum voltage to lift this disc up. Okay, so now as this disc is placed on the capacitor, the disc gets charged. Okay, the electric field on the disc is given by E, which is equals to V upon D, that is the voltage and the distance between them. Now since there is an electric field generated, the charge is transferred on the disc. So the charge transfer on the disc is, that is the charge transferred will be equals to Q, which is equals to C into V. So for the capacitance of parallel plate capacitor, we have the equation epsilon naught A upon D. So Q, the charge carried, will be equals to epsilon naught A upon D into V, where A becomes the area. Now since this is a circle, we have the area is equals to pi r square. So we can write epsilon naught V upon D into pi r square. That is the charge obtained by this capacitor. Okay, what is this? Question number 9. A capacitor is made up of two circular plates of radius r each, separated by a distance d less than r. The capacitor is connected to a constant voltage A, thin conducting disc of radius r much less than r, and the thickness t much less than small r is placed at the center of the bottom plate. Find the minimum voltage required to lift the disc if the mass of the disc is m. So what we have here is, we have two capacitors out here which have been connected to a voltage, to a voltage. Now there is, these capacitors are circular, okay, and the radius of them is r. They have separated by a distance d, which is of course less than this r. The capacitor is connected to a constant voltage. A thin conducting disc of the radius r, there is a disc out here which has radius small r, which is less than this capital R, and the thickness t, which is less than the radius of the small disc, is placed at the center. So the voltage which will be required to levitate, like to lift this disc, if the mass of the disk is given as n. So suppose the disk is touched to the bottom of the capacitor. Now due to this the disk gets charged, and as a result of that there is some electric field generated on the disk. So electric field on the disk is given by field on the disk. Okay, it is given by E, which is equals to voltage upon the distance. Now let after the charge Q prime be the charge transfer, be the transferred charge to the disk. So the total charge transferred on the disk Q prime will be equals to, we have capacitance into voltage. Okay, so for capacitance of parallel plate we have, so for parallel plate capacitance we have the formula C is equals to epsilon naught A upon D. So earlier we found the Q, the charge on the small disk. So Q prime is equals to C becomes epsilon naught A upon D into V, which will be equals to epsilon naught V upon D. This A is the area of the disk, which is a circle, so that area becomes pi r square. So pi r square. Okay, this becomes our equation. Now the force acting on the disk is given by Q prime E, which is equals to, Q prime is given by epsilon naught V D pi r square into the E. Now here the electric field intensity is given by V upon D, that is voltage upon the distance, as we calculated earlier. So the total force becomes epsilon naught upon D pi r square E, that is equals to V by D. So this is the total force which will be acting, that is, if we calculate the entire thing we get epsilon naught, here there is also another V, so it becomes, Question number 10. In a given circuit, initially K1 is closed and K2 is open. Then K1 is open and K2 is closed. If Q1 and Q2 are the charges on C1 and C2 and V1 and V2 are the voltages respectively, then charge on C1 gets redistributed such that V1 equals to V2. Charge on C1 gets redistributed such that Q1 equals to Q2. Charge on C1 gets redistributed such that C1 V1 equals to C2 V2 equals to C1 V. Charge on C1 gets redistributed such that Q1 plus Q2 equals to 2Q. Now firstly we have the circuit given here. We have two cases. First case, K1 is closed and K2 is open, and the second case, K1 is open and K2 is closed. So in the first case, when K1 is closed and K2 is open, the current flows in this circuit. Okay, as a result the potential is applied across the capacitor C1, and this uncharged capacitor C1 gets charged. Okay, it obtains some charge. Now as we move on for the second option, for the second thing, that is K1 is open and K2 is closed. Now this thing is open and this thing is closed. Okay, so the circuit gets disconnected from the voltage, and then we have is the circuit flowing through the two capacitors. This C1 is charged and this C2 is uncharged. So this charge C1 shares its charge along with the C2, as a result of which both of them will get the same charge. Initially when C1 was getting charged, the charge on C1 was given by Q1, which is equals to CV. Now after it has shared its charge with Q2, both of them will attain the same potential, so that is V1 will be equals to V2. So hence the charge on C1 gets redistributed such that V1, the potential on charge V on the capacitor C1, is equals to V2, that is the potential on the capacitor C2. So A is the right option. Question number 11. In figure, two positive charges Q2 and Q3 are fixed along the y-axis, exert a net electric force in the positive direction on a charge Q. The fixed of charge Q fixed along the x-axis. If a positive charge Q is added at x, 0, the force on charge Q1 will be. So there are two charges along the y-axis which are exerting some force on the charge Q, which is on the x-axis. Okay. Now what if we suppose if I kept a charge Q out here on the x-axis, whose coordinates are x, 0, then the force on this charge Q1 will be. Now firstly, here the Q1 is in the negative direction, so we have the charge on new Q1 is negative. So of course there will be a point of attraction, and this Q1 is placed in the positive direction. It is the charge on this is positive. So of course there will be a force of attraction between them, and that force of attraction will go on increasing as it will move on along throughout the x-axis. So our options are: shall increase along the positive x-axis. Of course it should be. We should see the next options as well. Shall decrease along the positive x-axis. No. While moving backward, it will increase. So shall point along the negative x-axis. Shall increase, but the direction changes of the interaction of Q and Q2 and Q3. Q with Q2 and Q3. So here from all the points we have, it will increase along the positive x-axis. So as the charge Q1 will move along the x-axis, the force between them, that is the force of interaction between them, will increase. Moving on for the further quadratic equation, the equation was 2L square minus 2LD minus D square equals to 0. So we have minus B plus minus under root B square minus 4AC upon 2A. So solving this becomes 2D plus minus under root 4D square plus 4 into 2 into D square, that is B square minus 4AC upon 2 into A is 2 out there. So the entire equation comes 2D plus minus under root 4D square minus 8D square. So upon this is 4. On solving we get D by 2 plus minus under root 3 D by 2. So L becomes equals to D plus minus 3 root 3 D by 2. So for the options we have D plus root 3D by 2. Okay. Two charges Q and minus 3Q are placed fixed on an x-axis separated by a distance D. Where should a third charge 2Q be placed such that it will not experience any force? Options are D minus root 3D upon 2, D plus root 3D upon 2, D plus 3D upon 2, and D minus 3D upon 2. So basically what we have here is, we have two charges Q and another charge minus 3Q, which are separated by a distance of D. Suppose this charge is A, this charge is B. Suppose now we have a charge 2Q. Suppose I place the charge 2Q out here, okay, and the distance between that point, suppose it is P to A, is given as L. So now for this P to be having no charge, it will, so that the point P will not experience any force. That means the force of attraction between them and the force of there will be a force of repulsion between this, and the force of attraction between P and B, and a force of repulsion between P and A. So for it to experience no charge, the force of repulsion and the force of attraction between both of them should be same. So we will calculate both the forces simultaneously, equalize both the forces simultaneously, and then we will come to a conclusion. Okay, so what we have here is the force of repulsion is equals to the force of attraction. Okay, so for the force formula we have Q1 Q2 upon 4 pi epsilon naught r square. Similarly here Q1 Q2 upon 4 pi epsilon naught r square. The charge Q1, this is the repulsion force, so the charge Q1 is, suppose we take it as Q, the Q2 will be 2Q upon 4 pi epsilon naught, the distance is L, so it becomes L square. Over here it becomes 2Q minus 3Q upon 4 pi epsilon naught, the distance r square becomes D square. Sorry, the distance r square, that will become L plus D the whole square, because it is combination of both the distances. It is going the distances from P to B. Okay, now solving the equation we get L plus D square is equals to 3L square. Okay, or we can also write it that A plus B the whole square, L square plus 2LD plus D square equals to 3L square. This brings you along 2L square minus 2LD plus minus D square equals to 0. Okay, we'll solve the further quadratic equation. Question number 13. Figure shows electric field lines in which an electric dipole P is placed as shown. Which of the following statement is correct? The dipole will not experience any force. The dipole will experience a force towards the right. The dipole will experience a force towards the left. The dipole will experience a force upwards. Now, as we see, there is an electric field lines which are passing through the dipole. This electric field is not constant, it is not uniform, hence it is varying. So therefore the electric dipole will always move in the direction opposite to that of the field. So if it is moving towards the right, the dipole will experience a force towards the left. So your correct option is C. 14. A point charge plus Q is placed at a distance d from an isolated conducting plate. The field at a point P on the other side of the plane is directed perpendicular to the plane and away from the plane, directed perpendicular to the plane but towards the plane, directed radially away from the point charge, and directed radially towards the point charge. Suppose we have a point charge Q that is given as plus, and we have an isolated conducting plate. So whenever we have a point charge, whenever we have a charge positive, whatever charge it has, suppose here it is positive charge kept at a distance from the conducting plate, the plate itself generates an equal and opposite charge on that plate, and as a result on the other side of plate the opposite charge is generated. So as a result, if this is plus and negative charge is developed on the plate on one side of the plate, and on the other side of the plate the positive charge is developed. We have a point P on the other side of the plane as well. So this point P, the electric field at this point P will experience a force which will be perpendicular to the point P, and it will be away, it will be directed away from the plane. So the option is A, it will be directed perpendicular to the plane and away from the plane. Question number 15. A hemisphere is uniformly charged positively. The electric field at the point on a diameter away from the center is directed A, perpendicular to the diameter, parallel to the diameter, at an angle tilted towards the diameter, and at an angle tilted away from the diameter. Basically we have an hemisphere out here which is uniformly charged, positive charged. Okay, this is uniformly positively charged. Now this is the dia. Okay, we have its center out here. The field at a point on the diameter away from its center, that is somewhere out here, the field will be directed perpendicular to the diameter. Always the field will be in the direction perpendicular to the direction of the diameter or to the direction of the charges. So it will be perpendicular, it will not go parallel, so it will be perpendicular to the diameter. It will not make an angle, so it will not tilt. Okay, the direction of the charge will be always in the perpendicular direction towards the charges. Question number 16. A uniform electric field E, which is equals to 2 into 10 raised to 3 Newton Coulomb inverse, is acting along the positive x-axis. The flux of this field through a square of 10 centimeters on the side whose plane is parallel to the YZ plane is 20, 30, 10 and 40. So what we have given is, we have an electric field E which is equals to 2 into 10 raised to 3 NC inverse. Okay, also we have a square whose one side given is 10 centimeters. Okay, whose one side along the positive x-axis, the flux of the field through a square of 10 centimeters. Okay, we have it 10 centimeters over here. So now, so what we have here is the side that is 10 centimeter. Okay, this plane, the electric flux lines passing through the square, this plane is parallel to the YZ plane. As it is parallel through YZ, Y and Z plane, the theta becomes equals to 0 because it is parallel. So the flux through the square is given by this formula ES cos theta, that is equals to E, which is equals to 2 into 10 raised to 3 into S, that is the side 1. So the total, this is one side, so the total formula for the side is, for a square becomes side square, that becomes 10 square. So converting it into meters, we get 10 raised to minus 2 meters. Okay, so that becomes 10 raised to minus 2 meters into cos of theta is 0. So solving all this, we get 20 n C inverse m square. So we have the answer A, 20 n C inverse m square. Two spherical conductors, each of capacity C, are charged by the potential V and minus V. These are then connected by the means of a fine wire. The loss of energy is 0, half CV square, 2 CV square. So we need to find the total loss of energy in the capacitance. Basically these are first charged by the same potential, and the capacity of the capacitance C of both of them is same. So we have the formula C1 C2 into V1 plus V2 the whole square upon 2 C1 plus C2. Okay, since both of them have the same capacitance, we can take it as CC. The voltage applied between both of them is same, so we can make it as VV upon 2 C plus C. Solving the entire thing comes out to be CV square. So hence we have the option CV square. Question number 19. A metallic sphere shell has an inner radius R1 and an outer radius R2. The charge is placed at the center of the spherical cavity. The surface charge density on the inner surface is. So basically we have two spheres, concentric. One is here and one is out here. Okay. The inner radius is R1. The outer radius is R2. Okay. We have a charge Q, that is plus charge, placed on the center of the sphere. Now the surface charge density on the inner sphere. So because the charge plus Q is placed on the inner center, the charge induced on the inner shell is negative. Because there is a positive charge, the charge induced on the inner shell is negative. Also the charge induced on the outer shell will be positive. So we need to find the surface charge density of the inner surface. So charge density on inner surface will be equals to minus of Q upon 4 pi R1 square. The minus Q because the charge generated on the inner surface is minus. So we have the option B, minus Q upon 4 pi R1 square. 20. Two identical capacitors are joined in parallel, charged to a potential V, separated and then connected in series. The positive plate of one is connected to the negative of the other. Which of the following is true? The charge on the free plate connected together are destroyed. The energy stored in the system increases. The potential difference between the free plate is 2V and the potential difference remains the same. Basically there are two capacitors which are charged with the potential V, that is the potential difference across both of them is the same, and they are connected in series. The positive plate of one is connected to the negative. So now we have two capacitors which are connected in series. So the total potential across the two connectors across the two capacitors, suppose it will be given by V double prime, it is equals to the potential across 1 and the potential across 2. So as we know, potential across 2 is both of them is the same, so we can have V plus V, that will be 2V. So the potential difference between the two free plates is 2V. The answer is C. Number 7. A capacitor of capacitance C1 is charged to a potential V and then connected in parallel to an uncharged capacitor of capacitance C2. The final potential difference across each capacitor will be C1V upon C1 plus C2, C2V upon C1 plus C2, 1 plus C2 upon CV, or 1 minus C2 upon CV. So basically we have a charged capacitance C1 which is charged due to a potential V, and then it is connected in parallel to a capacitance C2. So we have basically two capacitances out here, one is here and one is here. Both are connected in parallel, one is charged and another is not charged. So when the charged capacitor comes in contact with an uncharged capacitor, it tries to pass on its charge to the other one, and so as both of them gets equal charge, the current passing continues till both of them attains the same charges. Now they have so both of them will attain the common potential. This common potential is given by the formula Q1 plus Q2 upon C1 plus C2, where Q1 is the charge on the first capacitance, that is equals to C1V, plus the initial charge on the second capacitance is 0 upon C1 plus C2. So we get C1V upon C1 plus C2. Here we have the option C1V upon C1 plus C2. This will be the charge. Further we calculate the force that is required for the disc to lift up. That force is given by Q into E, where Q is the charge. The charge we have found it earlier, which is equals to epsilon naught V upon D pi R square into this E is given by V by D. So the entire thing becomes epsilon naught V square upon D square pi R square. That is the total force. Now if the disc is to be lifted, we need that the total force must be equals to the weight of the disc. So that is the total force we have is epsilon naught V square D square, which is equals to mg. So we calculate V, the voltage, the minimum voltage. At the minimum voltage is given by under root, calculating all the things, D square upon pi epsilon naught R square. So this is the minimum voltage required to lift the disc up.